Good afternoon. My name is Haiwen Bian, and I'll be presenting this end of the quarter report for the Virtual Neural Lab topological analysis, and specifically topological driven insight into naturalistic animal behaviors, mimicking by a neuromechanical agent. So, a great deal of what our lab does in the past is about key point tracking. It's about trying to model animals' behavior about ethology. And we can see really nice dimensionality reduction graph here that it shows that certain areas are correlated with certain behaviors. That is really nice. But then we all know that the brain doesn't control the key points directly, so there must be something else. So we know that the brain is situated in the body. We know that the central nervous system gives motor commands to the skeletal system, and the skeletal system, the musculoskeletal system, does force control with kinematics and interact with external environments. And in the process, we have sensory feedbacks from all of our sensors. We can see from vision. The fly has its winds to detect different things, and then with contact, different type of signals coming back, some feedback from the environment. And at the same time, our body does feedback with us as well, with mechanical feedback. So what Neural AI or the Virtual Neural Lab does is we try to mimic animal behaviors using something we call generative inverse kinematics. And what it does is once it mimics the agent's behavior with deep reinforcement learning, we can generate novel behaviors that's outside of these training sets even or even switching intentions. And in the essence, trying to study these is from a logical perspective, but then everything in virtual. And this is a quick schematic that's illustrating that we're trying to do real animal and virtual animals alignments. Um, in here, we have multiple animal bodies, but for this studies, we'll basically focus on the rodents as it is one of our first bodies. And this is the main schematic of what our VNL policy looks like, where we have the future 5 steps of expert trajectories recorded from real animals, real rodents, and then this is given mapping into sort of this motor intentions in the latent Z space, and then decoded by this biomechanical realistic decoder that is trained to give actual biomechanical realistic movements. And the goal here is that maybe we can even swap the encoder to some, let's say, task-driven deep reinforcement learning and eventually see what are the motor intentions and does it perform the behavior with a biomechanical realistic action. So some data looking at the inputs. This is from Stack, which is basically how we get from real animal rodents recordings to actual virtual animals, solving the inverse kinematics problem. And this is by our collaborator Diego at Harvard University. And as we can see here, that there are also neuronal recordings on these rodents, which later on can do neuronal signals analysis. And from all these recordings, we have a very wide diverse set of behaviors. We have fast wall walking, a lot of rearing, all kinds of behaviors. So the natural question is, can we do behavior segmentation? And even more, can we segment behaviors maybe from the intentions that we were looking at? So this brings us to why using topological data analysis at all. Why can't we just use dimensionality reduction, right? This is a U map being performed with a sliding window of 20. And keep notice that there's a caveat here where there needs to have specific tunings. Let's say the sliding window of 20. There needs to be specific tunings for the dimensionality reduction technique for it to actually work. And in essence, all dimensionality reductions are distorting the data in some sense because doing projections in one sense or the other. And comparing with TDA here, where this is using just doing plain persistence homology upon each clip space, and then we're comparing clips based on these persistent signatures using 2D Wanderson distance as a metric of distance sensing. And just to show a quick example here, this is a fly, not our target audience here, the target audience of this model here, but then it does illustrate something that if we look at similar clip and dissimilar clips, there seems to be different gait cycles, at least in the behaviors. And this is, remember, all done on the intention space. So this is quite magnificent to me already. So from 4 and 5, we see that it somewhat have similar gait movements, while 0 and 2 has very vast different. Like 0 is a little bit more steady, and then 2 is doing all of this. So to introduce some general data pipelines for each of the clips, so we have 500 frames here, and then it says times of the observation, but it's actually a stacked observation of 5 states. And then we transform that into intention space and then do delay value. So to go more precisely, we have the state space, we have the encoder from the previous graph, to give us a intention that has, this is for one clip, remember, that has 500 times 60, assuming 60 is the intention latent dimension. And then after we do tokens embedding, so in this space, we do discrete Morse graph identification of stable manifolds that allow us to eventually get different pathways out, which I'll explain later. And these pathways, we can put them back into the original intention space, get these intentions, identify these pathways, and then cluster them using Wanderson distance again, and then using some first giving the metric using distance metric using Wanderson distance, and then cluster them somehow, which will give us behavior segmentation. So this is a general pipeline. And then some method overview. As of the current moment, we have two methods testing. The first one is using persistent homology directly, and then we get the most representative or the most persistent hole in this, most persistent H1 homology class in this intention, this topology induced upon the intention, and then extract it out with cohomology. And in addition, just to serve as a better analogy with what we do later with discrete Morse graph, we have a distance to metric to respective density of the data. So it's a K induced one, and then we have our matrix that essentially just accounts the factor of this weight. And then the second method here is discrete Morse graph. And then it's, again, it's the first original graph was induced by a KN and then weighted by a binarized Descartes, binarized Descartes index, which is looking at, basically with each intention, we are binarizing it, to ones and zeros and then comparing it in that way. However, we found that this is not a very, efficient method, which will later on be switching to using Descartes directly looking at each neighbors. And then do notice that we have using the negated of this similarity, this for a technical reasons that we want the vertices to come in and then the vertices actually flowing to the edges, which I'll explain a little bit. And then to the actual discrete Morse graph, just some quick introduction back onto TDA stuff. We try to essentially draw this ball in persistent homology and then try to induce difference, try to reason about the shape. So this is a really nice visualization here, which is used in courtesy of Donald His group, which I feel like is a really nice representation of what persistent homology is doing. It's growing this ball, and then we're trying to recognize the click complexes was in between, and then eventually reason about the shape of it. And then with that, with this growing persistence module, we're trying to do something further. We're trying to reason about different manifolds. So when we're inducing a discrete gradient field, a discrete Morse field in this sense, we can have different manifolds that lives in it. And then this graph is a really nice illustration because we can see that the stable manifolds usually we have two critical simplex flowing into it, and notice that in the discrete in the convention of lower star filtration, we're always looking at the functional values from high to low. And so in here, in the stable manifold, we have we have these two triangles or these two critical simplex flowing down into this one critical simplex or this edges. And then in the unstable one, we have the reverse where this one critical simplex is flowing out to these zero critical simplex. So one is sort of flowing into it and one is sort of flowing out to it. And then since we only want the one skeleton directly, so we wouldn't really consider the triangle cases, and also because we want the vertices to actually come in first. So we do the negated of as what we previously we show, we do the negated version of the function in the sense that we can have this order reverse. So we can have this edges flowing actually into this one simplex flowing into zero simplex, and then not considering about the triangles directly. And then when we're actually doing it, we do it with a minimum spanning tree or minimum spanning forest in some sense. And this one of the features is called negative edge, which essentially we're looking at where we're looking at this edges that's connecting to connected components, and then chasing up to its representative through roots. So these negative edges are the critical ones that's in theory being proved to have equivalent effect of topological changes in the space, and that's what we're trying to find, which is currently a drawback of our current implementation because our current implementation is just keep tracks of the most persistent. One thing is that we're looking at edges with only certain persistence threshold, so above certain that. So the current setup only tracks the persistence tracks from the persistence threshold that's above the edges that's above the persistence threshold, which makes us having a full MST in the end, and neglecting that there is probably some component that's not connected, which basically we're looking at all the on the contrary of negative edges that connects to components, we're looking at positive edges that's closing up in one big connected components, which is not exactly what the discrete Morse graph is trying to do, or what we are trying to do here, which we'll fix later in the later on implementation. And some quick results here, even with this flawed implementation, we can see that we can identify the most persistent loop. This is a UMAP embedding again on the right and the PC on the left. And then we can see that we can have the most persistent loop with persistent cohomology, and then using the discrete Morse graph to identify these holes. And some rendering example, we can see that from looking at the differences in the distance to measure persistent homology and the inclusion driven, so the classical persistent homology, they pretty much identify the same thing. Where if it's on the loop, it's majorly some cyclical movement or cyclical behaviors. And I'm glad that it's actually reflected somewhat in the intention. And you can see that some of here is not exactly cyclical formation as we were thinking about like walking or doing like different type of gaits. This is more of some of them is actually even just standing. This is generally because of the checkpointing's quality, having different tip tap motion in the toe when rearing up. It's an energy control costing, which so basically the quality of the checkpoint might cause this, and then switching later with a better checkpoint may solve this issue and identify only gate or cyclical formation clips. And this is what we have from the discrete Morse graph, where we see that from these long ridges are so it's basically from all the paths that we have been identified with the critical edges, we take the maximum for each clip, and then we can see that they're all sort of trying to look at these even for different clips and then very vastly different walking clips. They almost identify the same intentions or the same gait that is walking, the more macro features. And then for the short ridges, we can see that so this short ridges is taking from anywhere from 10 to 20 vertices. We can see that it's all these diverse intentions, these transition intentions that's happening to different behaviors in the clip. And then to the main course of what we're actually trying to do, we try to do behavior segmentation. And then our pipeline show that it sort of clusters some different type of behaviors together. And then comparing to just a control we did in the Euclidean space using k-means, they just basically just group things by Euclidean distance. And from rendering, we see that our pipeline is a little bit better in this sense, even with the flawed discrete Morse graph setting now. And this is when clustering with three components, we can clearly see that there's a walking one collection, there's a rearing collection, and then there's just a stationary collection. And then with increasing the number of clusters, we see even more where there can be even sort of this transitional within. So this is a PCA rendering, a transitional change in the PCA from walking to rearing, and then later on back um, to grooming or slow walk and then walking again. And so this is all the result I have for the end of the quarter presentation. Thanks for listening. And then we'll be making more changes to the implementation and later on for getting an actual correct discrete Morse graph out. Thank you.